we're trying to figure out.
I can't match dates to things. I can only imagine faces. I mean, I've never formally asked them their name or had a conversation or something like that.
Okay, yeah, you never actually talked. You never talked to me. Alex and I sometimes talk.
Very quiet.
You contemplate.
You're lucky I'll talk to you guys. You're lucky enough to be on my circle.
You talked to Letty. Letty's trying to get out.
Oh yeah, I didn't even talk to you guys directly. I saw That's exactly what happened.
No, I had to. When we were saying final semester quizzes, right? Basically, we talked to Rachel.
Yeah.
And that's how we got to do it. And then because we found out we were both friends and we had to have the same class.
No, I remember when I started talking to you guys. Well, not you, but Adam.
Yeah.
We had the orbital teacher.
Yeah.
What's her name? Whatever. McQuaid.
Yeah, we all played together.
Yeah.
And it was you, me, first one, Misha.
Yeah, I remember that. Levy, yeah.
Yeah. Oh, yeah, Levy was there too.
Yeah.
Really? Levy was there?
Yeah.
I swear you don't remember Levy.
I remember he's
Alright, everyone, let's try.
He's not a major anymore.
Just kidding. Let's see, I know we're all antsy. It looks like a low show Wednesday, right? Break, yeah. It's a late show Friday. It's not no show Friday, it's a late show. I don't know why you guys are always late, but okay, whatever. A class business. Got your homework 7, who cares? Is this, again, a no name? Look familiar? So if it looks familiar, you don't have to, so I have like 5 or 6 people who didn't turn in their homework, so I don't know whose this is. So if this is yours, more accurately, I'm playing it because you got an empty blank by your grade, so I'll leave that up here. Or just come by office hours. I didn't get a chance, here's your homework 7. If you didn't pick up your test, I have those, and one other. And again, with your grades in here. Now, there were 2 people that actually had blanks where for homework grades that they actually had it graded. I think what happened is, you know how it gets when the staples get like stuck together. And I think the guy graded it, but then he did 2 at once. You know, wrote down the grade and pulled 2 over. I think that's what happened. So double check those, all right? Because missing a whole homework isn't lethal, but it ain't good either. I also checked for errors. God knows, you got a 50, I accidentally hit a 4, that's entirely possible, but anyway, so you have that. And we did catch 2 mistakes. Let's see, next Friday, this coming Friday, I'll go over things I saw, problems on the test, so that I can, want to get in your head a little bit better. It's probably a bad thing, but I'm still the guy writing the test, right? So you have to live with that. And so I'll go over again what I thought, where it's not connecting. Because God knows test 2 is going to be heavily represented on the final, because that's really most of this class, especially what we're doing now. And then we kind of, as I mentioned, we washed it all up with a bunch of this and that, and it's not really even all that fun or interesting, but whatever. What else am I saying? So, a homework set again, I'll sign one today. Kind of hate that it spills over through. No option, right? It spills through spring break. I haven't written it yet, sorry, but I will get it up later tonight because I don't want you to, I'm not going to put it up Wednesday next week. I guess I could, but then I'm taking your spring break, and I don't want to do that. So, even though most of you don't start till Wednesday up, so I can tell by the number that are put under my door after in the class. So, any of you have questions? We're okay. Looking half asleep. I know last lecture was probably kind of boring. I was kind of, it's just like blah, blah, blah. It gets a lot more interesting here for the next lecture and a half. This part actually gets kind of cool where you calculate how far reactions go and how you can, we can actually mathematically prove the Chevrier's principle. And that'll be on your homework. Now, what you're going to need to do, though, is that the equations are complicated enough that I'm not even sure how to solve them, alpha plus 2 to the 3rd power divided by alpha 1/2. I mean, I actually don't know what to do to solve those at this point. Maybe I did in high school, but I don't know. So when you run into those questions, what I'll have you do is just use Mathematica online, because, I don't know why they did this. It's like shooting yourself in the foot, but they put Mathematica online for free. it's not like as good as the version you buy, but it's good enough for this class. So I'll send you links to the website, and I'll give a couple of examples on how to use it, with examples that are just trivially different than the ones you have to use. So it'll be easy. But the equations, again, are complicated enough, again, for how far does the reaction go, what happens when I pressurize a system, that will be a Le Chatellier principle deal, that you want to do it that way. I mean, I don't think we have a choice. All right, blah, blah, blah. So review last time. Now, don't write this down quite yet. Just wait 1 second. You know that's because I'm going to change this. Let's do the change of reaction. Sorry, I already changed myself in the corner. Change in reaction G. And of course, we're going to have A goes to B or whatever. So I'll just put a generic I there because I don't know, AB goes to CB or whatever. Now, this is what I don't want you to write down, per mole. Remember that per mole, that would just be the same thing as the chemical potential. All right, that's all fine and good, but if I do this though, remember this is how we started out last time. If I do that, chemical potential times moles, joule per mole times moles is now joules, so this is no longer that little, sorry, this is using OCD. Really getting bad about that. Should probably be able to head up here, but there you go. So that's where we started out last time. And then we introduced this concept, the extent of a reaction change, the number of moles per I. So we have 2 moles of A reacting with 3 moles of B goes to blah, blah, blah. The 2 and 3 are this guy, the stoichiometric coefficients. And so we represent the change as a single generic variable, and that's the extent of the reaction. I said that last time. And then we can say that the change of G, I'm doing it right this time, is the same thing. I'm just going to replace the change in N as so multiplied by the stoichiometric coefficient, which is kind of more sensible. And then remember that the change in, let's do this as a slope now, is equal to just the same thing. I'm just writing the same thing, so maybe you don't even want to do that. Okay, and the point was that as I drew some examples, several examples of this last time, we wrote down how G will change in the course of a reaction. This goes from 0 to 1. 0 did react, 1 has reacted all the way. What you're going to figure out, probably not today, I think because I'm going kind of slow, is that you're going to figure out when this doesn't go to 1. Right? Not all reactions have 100% yield, and nor should they. So, and that was an entropy effect, if you recall last time. So when this guy is 0, these stoichiometric coefficients are not magically 0. That's the 2a plus 3b goes to 1c and blah, blah, blah. Those are fixed, so that means that the chemical potentials have leveled out. So the product minus the reactants is 0. Once that's happened, everything stops because you're at equilibrium. And nothing can be changing in equilibrium. Except little examples like a snowball, ice cube turning to a sphere eventually. And anyway, who cares about that? Okay, let me do, again, I'm just reviewing last time, so this is a little boring. And I know that it probably is a little irksome how I can kind of switch between chemical G's and chemical potentials. I'm kind of doing it like the book, just because in case you're actually reading it, I'll write my own book. I'm really tempted to do that. I mean, I've got so many freaking notes that I can't stand you guys buy, or did you buy, a $200, $250 textbook. What was that? Was that torrent search? Anyway, if I was a book dealer, I think I'd be kind of freaking out. Okay, so again, last time, here is our activity. And of course, this is the pure partial pressure of B. And I need to bracket that off because this has been multiplied by the stoichiometry of B. I'm going to do the same thing for A, but I'm going to subtract it. Again, number in the back of the book. This will be the formation, G, because we're at constant temperature and pressure. And remember that question on the test. You can change temperature and rerun your reaction, meaning that it is meaningful to think about how G changes with temperature. It's just that when you figure out what temperature you want to run your chemical process at, you then hold it still. But you would do that just for safety reasons, if anything. Okay. I'm sorry. Because I'm talking about something different. Yeah, thanks for catching that. I have to write a handout, right, if I screw up. That's actually where all my handouts came from when I screwed up in previous classes. So now here's the cool thing. I think it's kind of neat. You are always fed in high school, right, products minus reactants. Everything is a product minus reactant. But at that age, you're more used to just like, okay, here's the formula, I'll remember the formula. Delta G is delta H minus T delta S. Okay, so that's the formula. In this class, I hope I've done this because we're getting close to the end. I hope I can show you why is that formula what it is. You know, question everything. And I guess it's easier when you're older. So why is there a minus? Why products minus reactants? Because A is being consumed. It's going away. The stoichiometry is negative because it's saying bye-bye. So that's actually why you get products minus reactants. Or if you don't care, it's products minus reactants. Now, the difference between this and mixing is that, and let's genericize this. Let's say activities. I'll come out here. Let's put this in the form of activities, which is good when we're talking about reactions in solutions. You know, like I have a solvent called methanol. I've added chemical A and chemical B. Which case, and then I've got my little sniffer above the solution that measures the partial pressure. I measure the vapor. What happens in the vapor? Chemical potential. I say, well, that's also happening in the solution. I see it changing. That's the chemical reaction. That's an awfully odd way to do things, but that is technically mathematically correct. Weird, but that's how we do it. And then, all right, if I do that, then I say that delta reaction G is, okay, so I need to include the stoichiometry. Warning, I've paid myself to the corner. So, I barely have room. Ln A of B to the stoichiometry minus ln A of A, activity A to its stoichiometry, bracket. And then this guy, of course, this is Hess's law. Delta reaction G naught. I'm not going to write that. Plus RT, natural log, activity is B to its stoichiometry. Okay, activity of A to its stoichiometry. There you go. Again, that's the equation you learned as freshmen. This wasn't freshman chemistry. But what they did was they told you to put concentrations. And activity is kind of like concentration, except that I know it's not the same because, here's exactly the definition. And I can imagine, yeah, if I have more concentration, I would have more partial pressure. My sniffer would measure more partial pressure. But that maybe not. And maybe they're not linearly related. Right? That's the failure of Raoult's law, is that this whole, this is all a vapor equation, right? And Raoult's law, when we were doing mixing, and I'm going to compare this to mixing so it all kind of makes sense, was that the mole fraction in the vapor doesn't necessarily match the mole fraction in the liquid. In fact, it generally won't. It won't be horribly off, but it won't be perfectly right either, which is what we're always trying to do. Okay, so more details on this, and then right towards the end of class, I'll actually start using it, and those will be like homework type questions. So let me write this again. I meant to not do it this way, but I screwed up. Putting myself in the corner. So I'm just writing this thing again. I'm going to do that little backward trick that I did before. Wait, what have I done? And, oh yeah, sorry. I just got my own way confused. I didn't as much time as I should have reviewed before class. Sorry, I'm just putting the same thing up again. And then we're going to compare this to mixing and talk about what drives reactions. And I've got a couple other little details to go over. anyway. Okay, so let me compare this to mixing G, and I'm going to start at the bottom and move up and put them right next to each other so you can see the differences. I've got 1, 2, 3. I don't know, I feel like I'm clever doing this. Maybe that's my problem. Okay, the mixing G was nRT. And I don't know, again, what kind of questions I may ask on the third test on this stuff. Because as I mentioned to you, I really don't care so much about Henry's law, Henry's law or Amy's law, because they're so inexact. Again, this is all about mixing. There we go. And then, of course, what I'll do is take out the mole fractions, and I've got Na RT, and mole fraction of A. So, and I'm just doing this to remind you about how these are similar and then how they're not. Because remember, the first step in getting things to react is to mix them, and that by itself has changed things, changed the nature of the game. And then what we end up with is RT. Yeah, I never wrote it down this way. I didn't really care to, and it's just not how you usually see things. So what I'm doing is I'm going to bring the moles to inside the natural logs, and then I can factor out the RT, and then natural log of A plus natural log of B is natural log of AB. So A, n sub A, times B. And now, in retrospect, I don't know why I didn't express it this way before. It's actually a lot easier than this. What's wrong with me? Anyway, so highlight the differences, and then talk about what drives a reaction. And I give a really cool example that's like insanely dangerous. Okay, for one, we're obviously missing this part, and that's just a straight up thermochemistry that comes from a chemical transformation. It's absent when you mix things, but when I mix things, I'm presuming that there is no chemical reaction. Remember, we were doing water and ethanol, my two favorite things, and don't ever say that too. So obviously, water is not magically being turned to wine. This one guy can do it, but most people can't. So you need bacteria and sugar, and so obviously there's no reaction occurring, so that term is missing. As for the rest of it, obviously it's incredibly similar. All right, instead of activities, I've got mole fractions, and let me just remind you. I think I'm going to write this down. Okay, a little bit of an aside here. Remember that Reynolds law said that the mole fraction in the liquid was equal to the partial pressure over the pure partial pressure. And again, that's just not right. That should be the mole fraction in the gas phase, but you know, you do things in solution generally, and in reality, see, that's why I hate calling Reynolds law a law, because it's wrong. In reality is you have to make the measurement, and then you have the activity, and then you can actually use these equations correctly. Reynolds law is a cheat that isn't really quite correct. And the other big thing is, of course, all right, so then we have moles as opposed to stoichiometries. Those are the same thing. Those are exactly the same thing. And as we do actual questions, and I'll give examples, and you'll have it on your homework. If we don't do it today, we'll get it by Friday. Remember that this is 3A plus 2B goes to blah, blah, blah. Right, the 3 moles, right? So when I give you questions and I say 3 moles plus 2 moles, 3A plus 2B goes to 3C plus whatever. The problem will be designed such that I added 3 moles of A, I added a mole of B, or whatever it was. I'm not going to do limiting reagents. A lot of people like to do that stuff. That's just a jerk move, right? I don't want to test your ability to notice I'm tricking you. That actually is a good thing to be able to do, but I'm not going to do it here. So again, these are the same thing as number of moles, right? So last bit, of course, is that A is on bottom, and it's not here. Again, that's because A was consumed. Products minus reactants. Or the stoichiometry is negative. Okay, well, who cares? All right, well, it does show you that there really is a lot of common with mixing and reacting, where really the only difference is the fact that A is disappearing. And again, that's what drives on the bottom. Other than that, it's really the same thing relative to this. Okay, what drives a reaction? Okay, so we want this to be as big as possible, right? Right? Positive, negative gain. Is this always positive?
Yes.
Right? So we want this to be positive for that to be positive. Oh, sorry. No. Oh, God, guys, sorry. Thanks for watching. Sorry about that. Fix it, right? That's a screw up. I had it in my head because I knew that's what I was doing next. Sorry. Okay, so positive, we want this to be positive because we want the reaction to go, right? This is when I'm tricking you. Have you figured that out yet? Negative, right. We want delta G. Remember, the one time we want to think negatively about our x. Oh, sorry. The one time we want to think negatively is about changes in energy. Energy does want to go down. You know, it is a little awkward to think that way, but you want this to be negative. So is this going to be big or small? Small, right? Natural logs of small numbers are negative numbers. If you get to 0, it's minus infinity. And so if I could make this zero, this is a reaction that would actually completely kill me and everyone on the planet because it would explode. So to do that, it looks like I need, what drives it? I'm always going to talk about driving a reaction, because why the hell am I doing it to begin with if I didn't want A to go to B? Because I want B because I'm going to sell it. So that'd be a high activity of reactants. And this is an A goes to B, so I'm talking about A. Now here's the damnedest thing. It's kind of funny how this works. So if I increase the activity of A, do I get more B? So, sorry, let me back up. Activity is obviously related to concentration. So if I increase the concentration of A, would that increase my yield?
To your point.
Yeah, it's not necessarily true. I mean, we like to think of reaction yields as being constant, and theoretically they are. So if I have A turning to B under STP conditions, then it doesn't matter what the activity should be. So in terms of yield, all right. But now, according to this equation, it does drive the reaction. What does that mean? It actually means that while the conversion may be the same, 75% yield, if I have more A to increase the concentration, I will simply get more B because a bigger number times the yield, 75%, no matter how much I have, results in more B. Energy is extensive, right? More B is more change in energy. So that's what it's really saying. So don't think of it as yield. If I drive a reaction by increasing the activity, I simply get more B just because I had more A to begin with. But that technically counts. So this is a little bit funky, think of it this way. There is another way to do this, and this is why you might want to change your solvent. So let's think rationally. A is a powder, a chemical I scooped out and I put it in my methanol solvent. Okay, if I use ethanol, maybe the activity went up. Okay, now that would be good, and that's why synthetic chemists change their solvents. Anyway, so but for those who don't like to think about this, okay, so this is one. Let's do two. Two other things is a high stoichiometry of B. Product. Okay, now again, all right, so that gets big, but I want that small. And a way to get this small, now A's vary from 0 to infinity, right? Zero to 1, 0 to 1. Okay, so this is a fraction. A is a fraction from 0 to 1. Okay, now tell me this. Let's say A is 0.5. A of B is 0.5. So we got 0.5, and let's say the stoichiometry of B is 1. In other words, 1 mole of A makes 1 mole of B. Let's say 1 mole of A made 5 moles of B. Which is smaller? One on the left or one on the right? Of course, we'll know about 0.5 times 0.5 times 0.5 times 0.5, I don't even know what it is. Right, but that's good. That's a good thing. Making the top small makes this top part small, makes a natural log of a number that's closer to 0, which is actually a big negative number, which means my reaction is going, which is why I'm doing it to begin with. Anyway, also notice that, okay, now here is a question I could ask on the test, and thinking about it. This would be a great true and false. Why? Okay, so now when I say why, I need to provide more guidance in terms of how I want questions asked. That's one thing I got out of the last test, because there's the 1 or 2 questions that almost all of you missed. Okay, so I asked this, so I have A goes to B and A goes to 5D, and I say, well, A goes to 5D is going to go better. And the question is why? Hint, I'm writing in my head, hint, think of enthalpy or entropy. Right, because delta G is enthalpy and entropy. I can say temperature too, but we're doing this at 25 degrees. Entropy or enthalpy, which is it?
Entropy.
Entropy, and I know that because it's inside of the it's inside of the natural log. Every time you see a natural log in any of these equations, that's entropy showing up. So you can see, you probably even have some in physics. Okay, now let me give you an example of that. It's really cool. But I swear to God, I really ought to turn off the camera because I'm going to tell you about something that's obscenely dangerous. And this is why I don't tell 5-year-olds this. I'd like to. This always happens. So there's a class of explosives called entropy bombs. There you go, entropy bombs. Okay, entropy bomb is when you get delta G to go real negative. So any reaction that has a real negative delta G is generally an explosive reaction, right? It's going to go real damn quick. Now, with a big negative delta G, normally you think of a big negative delta H. Because this is a bomb, and bombs get hot. And that I can imagine they would, because that's the entropy of the outside getting bigger. And the entropy of the inside probably got bigger. Well, that's a really big negative delta G. But I can have a neutral delta H and a really positive delta total entropy change, and that works too. It's just a little unusual. But if you can make this, which you can, that's why you shouldn't do it. Let me show you. This is I had trouble drawing this. It's kind of complicated. My head hurt a little bit. I'm not an organic chemist, obviously. I do a lot of synthesis in my lab. Okay, this is acetone peroxide. And this is a good example of A goes to B. Actually goes to 3. And I believe that this is this is a liquid, and this is a gas. Because the amount of energy released off the delta G. Okay, this is actually thermochemically neutral. This reaction, shouldn't put it that way. Enthalpically, it's neutral, but the entropy gain is gigantic. Especially a liquid going to gas, that's already a giant gain in entropy, but just there's more to it than that. I don't really know why, just because of the measurement. And so again, big positive change in total entropy. So this is actually an incredibly powerful explosive. It is actually, I'm not going to write this down, almost twice as powerful, not quite, just a little bit shy of twice as powerful as TNT. So that's a really big thing. It's also known as the favorite weapon of suicide bombers. This is the chemical they use because acetone is easy to get a hold of, and all you have to do is oxidize it. That's also very easy. Potassium permanganate will do it. I know lots of stuff will do it. The only problem is, and here's the damnedest thing, suicide bombers are scary. Scare the hell out of me. But most of them have failed in their missions. Most of them kill themselves because this is one of the most unstable compounds in the world. Suicide bombers are actually more likely to blow themselves up before they hit their target, wherever they're going. They will die on the way. And that's why more people haven't died of suicide bombers, because of the instability of this compound. Anything will set it off. If you look at it wrong, it will set it off. If the wind blows on it, it will go off. It's nice and powerful, but it's so unpredictable that it is actually illegal in every country with the government for it to be used by demolitions experts. So you think, well, okay, the guy has a license because he's been trained in explosives and you need to take down a house, or you blast through building a highway, you blast through the mountains. I used to live in the mountains, and everywhere you drive, you can always see the mountains being cut away to make room for the road. Oh, that person should be able to handle this. No, no one is allowed to handle this compound because it's just far too dangerous, and no one does it. So, okay, yada, yada, yada. So, okay, now it gets a bit more interesting. I know it's been a little bit dry. But now we get to the part where you can actually calculate how far a reaction goes. And start doing examples. They are a bit complicated, but they're not. I have this little formula for how you set these up when it comes to calculating how much a reaction goes. And you just follow the formula, and it's really not too bad. So reaction constants. So again, I'm fixing all that garbage you learned in freshman, which ended up being wrong. Okay, so remember that as I did last time, reaction G, we did extended reaction, and I did things like that. And it looks like G, DE, I know I'm missing my delta, whatever, 0. Okay, now either the change in reaction coordinate can be infinite, or the reaction G is 0. Well, this goes from 0 to 1, so I don't think the change is infinite. Besides, it's a partial. So a partial is actually 1 over infinity, not infinity. So that means that my delta G is 0. So at equilibrium, again, constant temperature and pressure, that's something you kind of screwed up on the test. At constant temperature and pressure, G is relevant, and so the reaction G is 0, and therefore, this is kind of neat, the Hess's law part, right, this is the part at time 0 before the reaction began, is equal to RT. And I hate to do this to you, but I want to introduce a new mathematical symbology because I run into it a lot, and if you haven't, you should know this as college graduates. God knows you're getting close. Yeah. I don't know. So, all right, one of you knows what the symbol is, right? All right, okay, yeah, it's a sum, except instead of sums, you've got crosses, right? It's a multiply everything. Now, remember that these guys are negative if they're reactants. So that's the one thing that you got to get in your head. And anyway, oh, wait a minute. No, I'm missing a minus sign, aren't I? Yeah, I'm missing a minus sign. There we go. And this guy is usually expressed at equilibrium. We say it's LNK. And before equilibrium, it's usually labeled Q. I don't care about that stuff. If you get a K and a Q confused, I utterly don't care. Q engineers have you probably have a different letter. Maybe it's positive in your world. I don't know. Something that engineers are actually. I know some of your chemists like, oh, those engineers already had this. I'm like, yeah, but they also had negative signs in front of everything. They got screwed over by it. Guys, really got to follow IUPAC. Okay, and then this is the equilibrium constant. And let me go over some factoids about it, and then, maybe we might get into some examples. So reactions, so pure substances. Okay, this is factoids about reactions with pure substances. Go ahead and put a star by this because a negative star. I'm not going to test you on this, and it's not going to be on homework. I utterly don't care. Because I'm going to stick with gases. When we do real examples, I'm going to stick with gases because it's easier, you can understand it a little bit better, and then instead of pressures, put in activities for liquids and solids. But actually, for solids, activities are always 1. Now remember, they don't have units. So if we're doing any of these calculations, right? So this guy tells me how far a reaction goes because it's only solvable. Sorry, OCD. It's only solvable because I hit equilibrium, right? So you can see where we're going. We're going to set this guy up, have it equal to this one, and then you're going to solve it. You're going to solve what this is, and then you know how far the reaction goes. Now, it turns out, some of the activities, and again, I'm going to cast these into partial pressure because we'll be doing gases because it's just easier. But if I was doing solids, reactions of solids, then all the activities are one. And this is for any of you geologists. I didn't have a geologist last class. I don't know if any of you, I don't think any of you are geologists, but just in case. You know, I'm kind of remiss to always stick with gases. But I also want to make sure that it's as easy as possible to tell the truth. Okay, so this is, anyone remember, this is calcium carbonate, right? Yeah, calcium oxide of CO2 gas. And so K would be the activity of, let's see, products, activity of CO2. Sorry, this is a little hard to see, I know. Okay, activity of calcium carbonate. And then calcium carbonate. Okay, these are one. Again, I have no units. So it's just equal to the activity of CO2, which is, of course, it's partial pressure over pure partial pressure. And that would actually be, oh, I don't want to give it away. There's a little funny thing. All right, now, you know that pure partial, I'll bring this up in a minute. I just want to start you thinking about this. Pure partial pressure of CO2, again, that's like it's easier to think about water. So the vapor in equilibrium with the water, and of course it's not 1 bar in reality. So I would think that normally this might be like the ambient CO2 pressure. And so what's kind of neat is you can see that the pressure of CO2 would matter. Because I can see that if I jack this up, then I'm going to change my equilibrium constant. And anyway, so because I'm going to stick with gases so much, I'm not going to test on this. It does come up when there's a part about phase diagrams where this is going to matter. So here it is. It's also going to be okay, but let's do something much more interesting, and it actually how to do these calculations. I'll just barely introduce to that. Now this part's really kind of cool. And I have to admit, I don't really understand it. I'm actually really quite confused by it, and I've never really found a good explanation. So that's when I was solid. Again, factoids about activities and these equilibrium constants of pressure. And I like doing this because, again, I will stick with gas types of reactions. Okay, so now let me write it this way. Okay, is equal to minus. You don't have to write this again. I've already done it. I'm just writing it differently. Slightly differently, it doesn't matter. Okay, so what does pressure do to K? Right, so I want to figure out, like this, as I mentioned to you, you can do all this stuff to figure out Le Chatelier's principle, the mathematics behind Le Chatelier's principle. You've always been told, add some products, you get more, add reactants, you'll get more products, add products, it shifts equilibrium to more reactants, right? So that's all you've ever been told. Now you're going to actually figure out how much, and also prove that it works in some of the homework problems. Okay, damnedest thing. What pressure was this calculated at? 1 bar, right, that's the standard pressure. So, does that change if the pressure itself actually changes? No. I don't get this. None. There's no effect of pressure. And why? I do kind of understand why. And by the way, I'm giving you a big hint for Beacon Lab. I wrote half the modules, so I know what you need to know when you're doing it next semester. I forgot, I don't know what's in yet. But, so why is that? So let me, this is one of your modules. Let's do A gas goes to 2B gases. Okay, now what happens is, let's think of products, let's do an energy diagram. I don't know whether that's G or A. Let's do extent of reactions. And you know that there's potential surfaces, right? And we like to put them like little parabolas, but now I'm going to double parabola because I have a barrier, because this is reactants and products. Okay, and again, gas phase understanding, and physical chemists got up until the 90s. Almost all of us studied things in the gas phase. Why? Because it's more perfect than liquid phase. So I don't like solvents getting in the way of my fundamental understanding. Solvents complicate things. That has kind of dried up because there's just not that much done in the gas. You know, of course, ammonia is made in the gas phase. That's horribly important, but it's also studied to death. So people don't really do gas phase stuff, but I mean, it's definitely the best way to understand things because you don't have the complication of the solid. Okay, now, I got gas in a box, and what does the gas do? Well, if I have one A, not a lot's going to have one A molecule. I don't know how I can do that actually, but let's say I did. That's, nothing's going to happen, by the way. You actually need gas. You need to fill the chamber with more and more gas. Why? Because A hits A, right? They're little bees, right? Occasionally they hit each other. And so the effect of pressure, which again I have to add gas, as they strike each other, it's either rattling out their reactant cage, and they can't go anywhere. But then they start hitting each other. Boom, you know, it hit it. Collision gave this guy a lot of energy, and of course it took it away from that. Whatever. So now it can go into products. I've got a product. No, we don't. It's a trick question. I'm telling you I haven't gotten anywhere. Any idea why? Now remember, energy can't be created or destroyed, and I'm right here. So, what's that? Say again? Well, it has this much energy, and now it's wandered over to the product phase. I'm telling you, you haven't really figured out what's happened yet at all. Any idea? It's a bit of a trick question.
The products in the same thing you come back.
Yeah, exactly. It has the same amount of energy just to rattle itself back. All right? Energy can't be created or destroyed. By the way you get products is another collision. That will drop it down, but it has to be there. And the same thing's over here. So what happened? Really nothing. So again, pressurization is good because it does give things enough energy to react, but they can shuttle back and forth, and the only thing that matters is where they drop down into. So that's kind of just it's a little hand-wavy way to explain why K does not change with pressure. But now this is where it gets really tricky. This is what I think like about the coolest thing that we'll do. It doesn't mean that nothing happened when you change pressure. And that's what you're going to calculate. It's really, really nutso. But you're going to do the math in your homework. You're going to see that this is exactly true. And this is all the Chatelain's principle being solved for. Now, if you've got A goes to B, as you will prove in your homework, that does nothing. There's no Le Chatelier's principle, pressurizing, doesn't matter. But when A goes to 2B, or 2A's go to B, all right, I promise you, K doesn't change. That doesn't mean nothing happened. So, sorry, again, we'll be at equilibrium, right? Because I want to know how much A and B I've got. And the reaction's done at equilibrium, right? And let me see whether, here, let me do this. I'll stick with 1. And let me point out that K is the partial pressure of B over the partial pressure of B star. Actually, I do need to get back your homework, so well, we won't really get into an actual example until Friday. Okay, so products, what am I doing? Products are on top, but I gotta square that, right? That's again, just go geometry. And then I've got to do the reverse for A. And that's to the first power for equation 1. Okay, so here's the neat part. A star and B star. Is what? Okay, now I just went off about how This guy is pressure independent because all the numbers in the back of the book, in the table in the back of the book, were determined, measured at 1 bar, for 1 bar, say. Now, sometimes those numbers had to be measured experimentally under non-STP conditions for practical reasons, but they took the measurement and then they... Dig up the butt. They didn't dig up the bodies either. Maybe we will in barely. Rocket dynamite. Yeah, so I'll just end with this part here. So now again, sometimes those numbers in the back of the book were measured at conditions that were not STP, but these, using heat capacities, we can turn that experimental realization to what we would have got if we could have made the measurement at STP, and that's what we're going to stick with. All right, now, any other question? Look at that. This is really tripping me out. I swear to God, someone is actually turning this on by remote control. I'm not freaking kidding you. I'm going to totally turn it off. I can. Anyway, okay, so now, again, blah, blah, blah. These numbers come from STP. And these are the pure partial pressures. I know I'm not going to win, but I don't care. That's what these numbers are. Now, I made a big deal about it. I had to take my water and get my sniffer and measure the partial pressure with like a mass spec or something. But the numbers in the back of the book say like water at STP, water vapor, the delta G was measured, but the pressure was not 1 bar. And if it was, if I could have STP conditions with 1 bar of water, what would you need to be wearing right now? So is the partial pressure of water vapor 1 bar at STP? Absolutely not. If it was, we'd need scuba gear. We'd be underwater, right? Percent humidity, 100% humidity means it's raining, right? That means water is in the air. All right, so the partial pressure of water vapor is not 1 bar. But you can make your measurement, get that number in the back of the book, and extrapolate it as though it was. Again, my question is, guess what these are? They're the same, and they are 1 bar. Okay, all pure partial pressures, all the numbers in the back of the book, the table in the back of the book, were determined under conditions of which they could be determined, but then they were mathematically fixed to what they would have measured if they could have made the delta FG, and enthalpies and all the blah, blah, blahs. They were back determined to what they would have measured at 1 bar. And that way, when I get this equation, I can just get rid of these and say PV squared over PX. And notice that the units actually still cancel. The way we do that is, if these are all 1 bar, I do this so that the units cancel. So this is 1 bar. So remember, the little circle means STP conditions. This is the pressure, and the pressure at STP is 1 bar. So notice it doesn't do anything, it just makes the units cancel. So real quick, if pressure increases in this case, in case 1, then this grows higher than, this one stays 1 bar. If pressure doubles, I would imagine this has gone up by a factor of 4, and this is only doubled. So my K, this is K has doubled. But my point K can't double. So guess what this does? What does case 1 do?
Go back to it.
It shifts to the left. Right, exactly. It shifts, the equilibrium favors more A. To raise this and undercut that, such that doubling the pressure kept K constant. Here's the hard part, but that doesn't mean nothing happened. A lot of things happened. B shifted back to A because there's too much B. And that's what Chevalier's principle. It's fighting changes to the initial condition. All things do it, including children, especially little kitty cats in spring. Okay, next time we'll do actual actions.